All right, AP Environmental Science. Good news today. We are going to start the last unit of the year, which is Unit 9. Unit 9, I like this unit because this is the unit where we get into like these big global problems. In fact, the title of this unit is called Global Change. And this is where we're going to talk about things like global warming, acidification of the oceans, the greenhouse effect, all these like really big problems that are facing our planet today. Not so much focusing on like smaller issues that we've been kind of dealing with all year, but let's kind of start off today with topics 9.1 and 9.2, which are on stratospheric ozone. Stratospheric ozone is a big global issue. So I think this is kind of a good one to kind of start the unit off with. Now, before we sort of get into what the problem is, I want to kind of review this, and this is, I think, is a good review for the AP test as well, is to just kind of revisit, our layers of the atmosphere, specifically these first two. Right? Those are the kind of the big ones that you're going to have to know anyway for the AP exam. So, here we have the planet, and of course, we've mentioned this multiple times this year that we live in the troposphere. Right? The troposphere is the layer of the atmosphere closest to the Earth. This is where all of our weather happens. Our airplanes pretty much fly at the upper regions of the troposphere. So we're pretty much, unless you're going to go in a spaceship and go into outer space, you're pretty much going to live your entire life in the troposphere. Okay. Now, right above the troposphere, we have the stratosphere. And kind of the big thing about the stratosphere that we should already know this, we've talked about it before, is that in the middle of the stratosphere is that layer known as the ozone layer. All right, so the ozone layer kind of rests kind of right there in the middle of that stratospheric atmosphere layer. So just again understand where these are in reference to the Earth. Troposphere is the layer closest to the Earth. Stratosphere is above it, but the ozone layer is within the stratosphere. Now, earlier in Unit 7, we talked about ozone in the troposphere. And we talked about that because tropospheric ozone is an air pollutant, right? It's a secondary pollutant that basically can cause photochemical smog. So that stuff is really bad. Like, we don't want that building up in our troposphere. We don't want that being in the air that we breathe in. It's a respiratory irritant, and it's not good for plants and all that type of stuff. So we don't want tropospheric ozone anywhere in the troposphere. But that was for Unit 7. We're not going to really talk too much about that in this unit because this unit we're talking about the stratospheric ozone. The stuff that's up there in the ozone layer, that actually is beneficial. In fact, it's a really, really important thing to have in our stratosphere because it's what helps protect our planet from all that harmful radiation from the sun. So as long as that layer is there protecting us, then life on this planet can exist as normal, and we shouldn't have any issues. But if something happens to that layer, that could have a major impact, especially on the living organisms on the Earth. Here's just another picture here of kind of the stratosphere and the troposphere. Again, down here is kind of where we live, right? And this is, again, where all that surface level ozone can build up. This is all of our tropospheric ozone. And again, I would highly suggest going back to Unit 7 and reviewing that for the AP exam. You will have to know quite a bit about photochemical smog and tropospheric ozone and all that stuff. But as far as the stratospheric ozone goes, again, this is located in the middle of the stratosphere, so you can kind of see where it's located. But again, its job is really to kind of block these different forms of ultraviolet radiation, and do know that it is ultraviolet radiation, which is part of the electromagnetic spectrum. Um, there are three different types of ultraviolet radiation, though, that you should know. They're called UVA, UVB, and UVC. All right, just starting on the right here, this is UVC. And one thing real quick, the differences between all three of these are basically their wavelengths. You might remember what wavelength is from chemistry class. UVA, UVB, UVC, they all have different wavelengths. So their ability to penetrate through the ozone layer is a little bit different. UVC, you can kind of see here, UVC doesn't really penetrate through the ozone layer. It's pretty much stopped completely. So those UVC rays never make it to the Earth, which is a good thing, okay, because it is ultraviolet radiation, and we probably don't want that stuff reaching the Earth. UVB radiation, for the most part, gets blocked pretty well by the ozone layer. A little bit of it gets through, and it really is kind of dependent on where you live on the planet. In some regions of our planet, the ozone layer is a little bit thinner than in other places. We'll talk about why that is in a few minutes. But if the ozone layer is thin, then that UVB radiation can penetrate through a little bit easier. Other places it really can't. So UVA, however, that one can pretty much get through. This is the reason why you go outside and you put sunscreen on. We put sunscreen on because we are being exposed to UVA pretty much everywhere on the planet. So, the ozone layer doesn't really block that very, very well. But UVB and UVC, pretty much it does, just depending on where you live. All right, now as far as ozone goes, it pretty much exists up in this layer all the time. This slide here is kind of showing you how ozone is produced. Make sure we do understand the chemical formula for ozone, which is O3. All right, so anytime you see O3, right, that's ozone. We did reference that in Unit 7. But this is showing us again how stratospheric ozone is produced. And this really is a simple diagram if you kind of think about it. So we'll start here on the left. Okay, here we have, this is an oxygen molecule, right? This is O2. There's plenty of O2 in our atmosphere, troposphere, stratosphere, it's all over the place. But O2 actually can react with ultraviolet radiation, especially UVB radiation. UVB radiation, which is fairly abundant up in the stratosphere, it actually can break the bonds of this oxygen molecule. And so what we end up having is these two little oxygen atoms, or in this case, they're oxygen ions. All right, because once they split apart, they have their charges, their negative charges. But don't worry so much about that. So this first step here, I want you to kind of be able to understand that, right? We have an oxygen molecule. If it's exposed to ultraviolet radiation, it'll just break apart, okay? Now, those two little oxygen ions are now free to go and bond to whatever they want to bond to. They could rebond to themselves and kind of reform that oxygen molecule, but they usually don't. They usually end up bonding to other oxygen molecules, like this one here, and forming an ozone molecule. So that's kind of what we're seeing here. We're kind of seeing, how this oxygen gas breaks apart to form the ozone. And this happens all the time in the stratosphere. All this ozone is building up and building up and building up. However, the ozone can also break down. So, anytime you have an ozone molecule, it also can react with ultraviolet radiation, and it can break apart into an oxygen ion and an oxygen molecule. So, this is kind of showing us the buildup of ozone, and this is kind of showing us the breakdown of ozone. And in most cases, these two processes kind of balance each other. The buildup of ozone and the breakdown of ozone those two things are normally in what we call a steady state. So as long as nothing disrupts the steady state, then we're going to constantly have that level of ozone in our stratosphere. All right. But of course, there are things that we do, anthropogenic things, that can disrupt the steady state. Now, one of the things that we do to kind of mess up the ozone layer is we release certain chemicals into the atmosphere that can have an impact on ozone. Um, Probably the most notorious chemical, and this is a name that you're going to have to know. It's called a chlorofluorocarbon. All right, we call them CFCs for short. Chlorofluorocarbons are a source of chlorine. These were chemicals that were heavily used back in the 1960s and 1970s. They were mainly found in refrigerants. So, like, the stuff that keeps your fridge cold. Okay, now nowadays, today, we don't use CFCs anymore. We use something else, and I'll explain that in a little while. But back in the 60s and 70s, we used these chemicals called CFCs, and that's what helped keep your fridge cold. They were also used in things like insect repellents and aerosol sprays and air conditioning units, but refrigerants is kind of that was one of the major uses of them. Now, the problem with CFCs, all right, and here in the upper left here, this is a picture of the molecule, right? So it's a carbon atom that's bonded to a fluorine atom. So, fluorocarbon, right? That's where the fluorine comes from. And we also have these chlorine atoms, right? So it's a chlorofluorocarbon. It's chlorines, fluorine, all bonded to a carbon atom, all right? Now, I'm going to make this diagram really simple, all right? So just pay attention. CFCs, when they go up into the atmosphere, when they're released into the atmosphere, they can react with ultraviolet radiation. And look at the picture here. Look to see what is happening. When ultraviolet radiation reacts with a CFC molecule, it causes the chlorine atom, or at least one of them, to break apart. Chlorine is really bad for the ozone layer because, if you kind of just look at these pictures, the chlorine atom has the ability to break apart the ozone. That's not normal. All right, ozone does break down naturally, but this is an anthropogenic way. We're putting chemicals in the air that also cause ozone to break down. So when that chlorine atom hits an ozone molecule, it actually causes it to break apart. And one chlorine atom can do a lot of damage. It says here, one free chlorine atom can break apart over 100,000 ozone molecules. So, I mean, that's really all you need to know. All right, when CFCs go into the atmosphere, they react with ultraviolet radiation, and they cause the chlorine atoms to break apart, and they are what causes the destruction of the ozone layer. So these chlorines are really bad for the ozone. They basically help to deplete the ozone layer, on an anthropogenic level. Now, what this can generate is something called an ozone hole. Now, above the Antarctic, down in Antarctica, the continent of Antarctica, the ozone layer has become extremely thin to the point where it's basically non-existent in certain areas. Now, one thing about the ozone hole above the Antarctic, just real quick here, I'm talking about, here's Antarctica, this big blue area here. This is this ozone depletion that we're talking about. The one thing about this ozone hole above the Antarctic, the ozone actually does thin naturally. It's without any anthropogenic causes. And in fact, it thins every single year above the Antarctic during the months of August and November. That's what we call the Antarctic spring. Remember, southern hemisphere is just the opposite of the northern hemisphere. So, like August to November, we would probably consider that to be fall, right? But in the Antarctic, they consider that to be the spring. So, remember that, that's important. Now, the reason why the ozone layer gets thin is because of ice crystals that build up in the atmosphere. And those ice crystals can actually contribute to the thinning of the ozone layer above the Antarctic. But that's the only place that we really see that happening is down there. So the ozone layer does naturally get thinner. But due to us putting a bunch of CFCs in the atmosphere, that normally thin layer of ozone is even thinner. It's thin to the point where there isn't any ozone. All right, so if there's no ozone above the Antarctic, or that area is very thin, then that allows really dangerous levels of UVB radiation to reach the planet, right, especially above the Antarctic. So what this graph is showing you here is basically this. It says here it's total column ozone. It's basically the thickness of the ozone layer. You'll notice here, like in the months of like October and November, it gets really low. All right, and that's a natural thing, but again, because of these CFCs, it's getting even thinner than that. So there's kind of a natural cause and an anthropogenic cause. So make sure we know both of those things. So again, here's this region. So back in the 70s and 80s, scientists started to get really concerned about this. This ozone hole was actually getting bigger, and there was fear that it could get so big that it would be non-existent, and it could spread to other areas of the planet. So, some of the issues that center around ozone depletion, if all this UVB radiation reaches the Earth, that's going to affect photosynthesis of plants. If too much UVB reaches the planet, plant photosynthesis gets disrupted heavily. So if you've got plants that can't photosynthesize because of too much radiation, that's going to really have an impact on food webs and food chains, especially in the Antarctic. But that could be eventually be a global problem. Eggs of amphibians, fish, and reptiles. And remember, a lot of these eggs of these organisms, they're not hard shell. They're kind of leathery. They're kind of soft shells. So that UVB radiation can actually penetrate through and kill them. So these types of species can really be impacted by too much UVB radiation, and it can also impact human health. Not that there's a ton of people who live in the Antarctic, but again, if this hole becomes bigger and it spreads, then we're talking about increased risks of cancers. Cataracts of the eye are caused by too much ultraviolet radiation. So again, these are some major effects. Now, efforts to reduce ozone. One of the things that the scientific community came up was basically a treaty that said, all right, we need to, as a planet, try to eliminate all of these CFC compounds. Like we cannot manufacture these anymore. We cannot put these up into the air. This was called the Montreal Protocol. The Montreal Protocol basically was 180 countries agreeing to ban over 90 some chemicals that all have CFCs in them. And the result of that has been really good because the amount of chlorine that has been allowed to accumulate in the air has become more stable. So we're not like putting any more of it up there. The problem is the chlorine that's already in the atmosphere that was put up there back in the 60s and 70s, that stuff is still there, and it kind of lingers. In fact, it takes up to about 50 to 100 years for all that chlorine to eventually get out of the atmosphere. So, I mean, we're still going to have this ozone problem, but at least by not putting any more of these chemicals into the air, we're not making the problem any greater. All right, so that's kind of a good thing. But again, we're stuck with this hole all because of something that we did, for decades. Another thing that we've done to reduce ozone depletion is we've taken CFCs and we've replaced them with other chemicals. They're called HFCs. These are called hydrofluorocarbons, and something called HCFCs. These are called hydrochlorofluorocarbons. The thing about these is they have taken the place of CFCs. So these are also refrigerants, okay? For example, these are the things that we use in our refrigerator today. The good thing about these substitutes is they don't lead to the depletion of the ozone as much, and that's mainly because they don't have as much chlorine. In fact, HFCs don't have any chlorine at all. Hydrochlorofluorocarbons do have chlorine, but there's less chlorine. So we're using these kind of as a substitute. So the good thing is, we're not putting those dangerous CFCs into the atmosphere anymore. The bad thing about these is that they're actual greenhouse gases, right? Greenhouse gases are things that trap heat. So it's kind of like we're trying to solve one environmental problem and we're kind of creating another one. So the best thing would probably be to not put any of this stuff in the atmosphere, but like we all like to go to our fridge and have a cold beverage once in a while. So like these are the chemicals that we use to do that stuff with. But this chart here kind of shows CFCs, they're ozone depleting chemicals. Though these are the ones that have been banned by the Montreal Protocol, and we've replaced it with these two things. Okay, so these are less ozone depleting. Right? HFCs are not ozone depleting at all, but again, they're still bad for the climate because they are greenhouse gases. All right, guys, that is it for today. I will see you soon. Take care.